Hey guys, welcome back to my YouTube channel. So in this lecture, we are going to continue our discussion on the residual systems, means digital electronics. So in this one, we have already started the number system. In the number system, we have completed the radix R. So the decimal, binary, octave and hexadecimal. So those kind of things, and how to find R's complement and R minus 1's complement. Those things we have already completed. So now we are going to start with BCD codes. So BCD codes is nothing but a simple another way of representing the things. So that will be some kind of things that we be usually following. So how to represent BCD codes and what are the things behind that. So let's see here. This is binary coded decimal. So if we have 25, so 25 in the decimal number, so which can be represented in binary as 1 1 0 0 1. So this is what this value will be 25 because 1 plus 8 plus 16, so that will be binary. So if this is binary, so in order to represent this in a BCD, we need to take individual bits, so 2 separately, 5 separately. So 2 can be how the 2 can be represented, that can be represented by 0 0 1 0, 4 bits we have to represent, and 5 can be represented as 0 1 0 1. Okay, so this is what the BCD code, because as we know BCD code will be ranging from only 0 to 9. Okay, so we can't represent 10 anything because it is a single digit, so we will club each digit and we will represent like this. So this is what the BCD codes. The difference between binary and BCD is like this only, so individual bits only we will taking. So this is packed BCD. Okay, so if we are to make it as unpacked, means each thing need to be represented in 8 bits. So for an example, this one need to be represented in 8 bits, so 0 0 0 0 0 1 0, then this one also 0 0 0 0 0 1 0 1. So this is called unpacked BCD. So these are something that may ask what if in my packed and unpacked BCDs. So you guys may need to know all the differences. Okay, so this is what the difference between normal representation in everything. So now let's see some chart of representation between different things is. So let me draw a table so that you guys are able to understand it clearly. So here we are going to analyze different things. So this is normal. We are going to calculate the BCD codes for the normal decimal. Okay, so for an example, here we are having decimal systems. Okay, so decimal systems here, decimal. So then we are going to find different, not only the BCD codes are many type of BCD codes, not only single thing. So all the some kind of weighted complements will be used. So I will be explaining you all things. So first one kind of BCD code is 8421. So 8421 is one thing, and then 2421 is another one kind of BCD codes, and then 84 minus 2 minus 1. So this is also one kind of code, and Excess-3. So these are majorly used BCD codes. I will be explaining what are each things. So don't worry. So first let me complete the table. So here we are just going to apply mathematics. So simple addition, subtraction only. So that will not be that much difficult to handle. Okay. So let's take a decimal system as it is BCD, right? So this is BCD codes. So this is BCD codes. So it will be from 0 to 9 only. So 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Okay. Okay, no worries. Let me keep this up. Okay. So let how the 0 can be represented in any of the system is system. So we previously see, right? So 2 power 0, 2 power 1, 2 power 2, 2 power 3. Similar to that, this is same. So this is same like this. So how this is can be represented is that which is normal binary. How we represent in a normal binary, that we can handle it here. So that is one thing. So but as it is BCD, we need to represent in 4 bits. So 0 0 0, then 0 0 0 1, 0 0 1 0. Okay, the thing is that if we multiply this number to the representative, we will be able to get this. If for example if we take this 0 into 1 is 0, 1 into 2 is 2, rest is 0. So if we add all things, we will be able to get 2. So that is what the thing. So similar to that, here they represent another one system. So we have to multiply the bits that are representing here, and we have to add so that to get this one. So here if you see, as we can clearly see, we can put 0 0 because each bit is multiplied this and added, we will be getting 0. Then how we can get 1? So here we have 1. So that the first bit is 1 and rest all the bit are 0. So how we can get 2 is that there is two possibilities for representing 2. Whether we can represent as 1 0 0 0 or 0 0 1 0 anything. But for now, let's take second bit as 1. Okay, so this kind of representation. So in 8 4 minus 2 minus 1. So this is one kind of representation. How we can represent 0 is that the same. Every bit can be made to 0. So we can get 1. So in order to get 1, we need to choose a wise number to get 1. So 8 we can exclude it, and let's add 1 to all the rest of the number. So if we make this, then how this can be represented is the 4 minus 2 minus 1, because all the 3 bits are 1, right? So if we add all the 1, we will be getting 1. So how can we add 2? So 8 can ignore and minus 1 we can ignore. So if we put 0, if we put 1 1 in the middle 2 bits, then we will be able to get 4 minus 2 as 2. So like this only we have to complete all the boxes resting below. So Excess-3 is nothing but in the normal system we have to add 3. So we have to add 3 to all the existing number. So if we add 3 here, then what will be the number? So just 3. So 3 is binary complement. So 0 plus 3 is 3. So 3 is binary number is 0 0 1 1. So 1 plus 3 is 4. 4's binary is 1 0 0. Then 2 plus 3 is 5. Then 5's binary equivalent is 1 0 1. Okay, I hope this is understood for you guys. So please pause the video and try to fill rest of the boxes. In the meantime, let me also fill everything. Okay, so let me first complete the decimal like a decimal normal binary representation for all the things. So 0 0 1 1 0 1 0 0 0 1 0 1 0 1 1 0 0 1 1 1 1 0 0 0 1 0 0 1. Okay, so let me complete the 2 4 2 1. So which is nothing but you guys try it. I also mark it this. So which is 0 0 1 0. So for this is representation for the 3. So which is 0 0 1 1, because the last two addition will be 1. For 4 we can represent as 0 1 0 0. For 5 we can represent as 1 0 1 1. And 6 can be represented as 1 1 0 0. 7 can be represented as 1 1 0 1. 8 is 1 1 0, and 9 is 1 1 1. Okay, I hope it is understood, right? So for this 8401, so let's take the for 3, how we can represent this? 0 1 0 1 0 1 0 0 for 4. For 5 it is 1 0 1 1. For 6 1 0 1 0. So please you guys please note and try it to complete this table by yourself so that you guys can able to understand it. So 1 0 0 1 1 1 1. Okay, for an example, if this for this number, if we add all the bit, so 8 plus 12 is 8 plus 4 is 12, 12 minus 2 is 10, 10 minus 1 is 9. So that is how we attain this part. So this is nothing but an excess carry. So we have to add 3 to all the number, and then we have to represent this one. So this is 0 1 1 0. So then this is 0 1 1, then 1 0 0 0, and here it is 1 0 0 1, and 1 0 1 0, and 1 0 1 1, then 1 1 0 0. Okay, so I hope this is able to, I think you are able to get this table, right? So this is how we have to represent the BCD. These are different types of BCDs that are available. So now let's see some different kinds of behavior that is happening here. So in the Excess-3 code, if you see these two bits, like exact the 4 and 5 are complement to each other, right? So if you take one's complement for this, this is complete, this is representing this one. So then this to this, so this is complement of this one, this is complement of this one. Similarly, this is complement for this one, and the last one is complement for this one. So this kind of representation, if the exact each bit is complement of this one, this code can be called as self-complementary code. So this is one of the important 1 mark question that asked already in GATE examination. What is mean by self-complementary codes? Okay, so they will give 2 bits and they will ask whether this is a self-complementary code or not. So on the time you guys need to able to answer it. So now you can see this one is also self-complementary code. As you can see, the both the bits are just a complement to each other. So that is a self-complementary code for each thing. So what is meant by self-complementary code is that self-complementary code. So in self-complementary code, the 9's complement of the number can be obtained by using 1's complement. 9's complementary. The 9's complement of a number can be obtained by 1's complement. Right? Because this is a decimal system that we have used there. So we could able to get the 9's complement of number by simply turning each bit. So that is what that they are saying. So by using 1's complement. Okay, so this is self-complementary code. In self-complementary code, the weighted complementary code, the summation of all the sum of weights will be equal to 9. The sum of weights will be equal to 9. For an example, if you take this one, if 8 plus 4 minus 2 minus 1, if you add thing, it will be equal to 9. If you add things, 6 plus 8 plus 9, it will be 9. Is Excess-3, that is we may not consider this as a weighted self-complementary code. So if the summation which is equal to 9, then we can call as a weighted self-complementary code. Weighted self-complementary. Okay. Excess-3 code is self-complementary code and also sequential code. So one of the important thing is Excess-3 is self-complementary code and also sequential code. You can see that there will be sequential bit of transmission will happen. This is also they will naming as a sequential code because of the things. So Excess-3 code is self-complementary as well as sequential code. So why it is sequential code is if we add 1 to each bit, then the next bit we can able to get it. If we add 1 here, the 1 plus 1 we represent 0 1, then 1 plus 1 we represent 0 1, then this carries here. If we add 1 here, then 0 plus 1 is 1, then is 1. If we add 1 here, then that is 0 1, then 1 is coming here, 1 is same. If we add 1 here, that is 1 1 1. If we add 1 here, all the bit is done and 1 0 0 1. If we add 1 here, next bit. So similar to that, if we add 1 to the previous bit, the next number we can obtain. So that is what the thing that we will call as a self-complementary code or not. So from this one, so let's think what are the things. So let me give some shortcuts. For self-complementary code, I am using SCC. For weighted self-complementary code, I am using WSCC. And sequential code, I am making as SC. Okay, this is sequential code. Okay, so let's name what are the code follows which are the thing. So if we add all the thing, it will resulting in 12 plus 14 plus then 1, that is 15. So this one will not be considered as a self-complementary code. Okay, because this is not called as a weighted self-complementary code because the summation will not be resulting in a summation of 9. So this one will not come as a weighted self-complementary code. So this one can be called as weighted self-complementary code. So WSS. This one is also weighted self-complementary code. Excess-3 was not. This is sequential code. This is sequential code. This is also sequential code. Because if we add 1 to the previous bit, it will the next bit we can derive from that. So we can call this as a sequential code. Okay. So self-complementary code. So this one is not a self-complementary code, but this is self-complementary code. So SCC, SCC, and SCC. Okay. So above thing which I represented is very important. So which order code follows which order scheming. So you guys please make a note of all the things. so that you guys will be able to understand it very clearly. So from here I am concluding the discussion on the BCD codes. From next class we'll be starting with some other 2's complementary addition and 1's complementary addition from next classes. So stay tuned guys. I hope this is very informative for you guys. So if you think that is very informative, please like, share and subscribe the channel. So stay tuned for the next lectures. Thank you guys.